Section 1. Predicting composite elastic properties using an ANN approach. Have you ever actually stopped to wonder why designing new, advanced materials takes so incredibly long? If you're an engineer working with short fiber reinforced composites, or SFRCs, you absolutely know the massive computational bottleneck we're talking about here. You've got a polymer matrix, you've got short fibers scattered all throughout it, and trying to accurately predict just how stiff or strong that final mixed material is going to be, well, it's a colossal mathematical headache.
And that brings us to the overarching goal of today's explainer. We're going to be diving into a genuinely fascinating 2021 paper by Menchez, Dashtabazerg, and Mirkalov. If you take a look at the unedited paper header right here, it reads, "A micromechanics-based artificial neural networks model for elastic properties of short fiber composites." Their mission? Basically, to completely bypass those painstakingly slow micromechanical simulations by training an artificial neural network, an ANN, to do all the heavy computational lifting for us.
So let's look at why this is so necessary in the first place. Traditionally, engineers have really had two main choices, and honestly, both have some pretty major drawbacks. On one side, you've got direct numerical simulation using representative volume elements. It's highly accurate, sure, but it is just computationally brutal. Especially when you're dealing with high fiber volume fractions or really complex architectural geometries. On the other side, we have mean field homogenization methods. Think of the Mori-Tanaka model. These are much faster, but they often struggle to accurately capture properties when you start pushing into those higher volume fractions and extreme aspect ratios. So the researchers basically asked a very simple question. Can we get the pristine accuracy of a direct simulation, but with the lightning speed of a data-driven model?
Moving on to Section 2. The solution, a two-step homogenization framework.
Okay, so to train a truly robust machine learning model, you need data. An absolute ocean of high-quality data, but without the bottleneck of running full 3D simulations for every single data point. To get around this, the team came up with an incredibly clever two-step homogenization framework. Step 1 is performing finite element analysis on unidirectional representative volume elements, or UDRVs. Basically, you're simulating a tiny microscopic block where all the fibers are perfectly aligned, pointing in the exact same direction. Then, Step 2 takes those clean results and applies orientation averaging using a Voigt interaction assumption. In plain English, that's calculating how properties physically blend when those perfectly aligned fibers are realistically scattered and rotated in the final material. This two-step process is honestly kind of genius because it completely unchains the model from the usual limitations of arbitrary aspect ratios or high volume fractions.
Let's dive a little deeper into how fiber orientation is actually defined mathematically. Check out Figure 1 straight from the paper. We have a unit vector here, labeled with that red P, and it represents a single fiber's orientation in 3D space. This vector is described entirely by just two angles, theta and phi. By taking these angles and combining them with a probability distribution function, the researchers can define a really sophisticated second-order tensor. And this tensor perfectly describes the mathematical spread and orientation of fibers within any given point in the material.
Now, Figure 2 brilliantly illustrates what Step 1 actually looks like in practice. It shows the geometry and the highly detailed spatial discretization mesh of those unidirectional RVEs we just talked about. Notice the very specific geometric scaling they used here to guarantee statistical representativeness. The RVE length is scaled to exactly twice the fiber length, and the transverse dimensions are scaled to 5 times the fiber diameter. They ran all these analyses assuming perfect bonding between the matrix and the fibers, and they applied periodic boundary conditions just to capture the true, pure, homogenized properties of this unidirectional block.
And here's where it gets crazy. They automated this entire process across a massive microstructural parameter space. As you can see outlined in Table 1, they varied absolutely everything. We're talking matrix Young's modulus spanning from 500 up to 20,000 megapascals, varying matrix Poisson's ratios, fiber stiffness pushed all the way up to a massive 100,000 megapascals. They varied fiber diameters, aspect ratios ranging from short to long, and of course a really wide sweep of fiber volume fractions. By writing a script connected directly to their simulation software, they just swept this vast landscape and generated a staggering 24,540 unique data points. That massive data set? That is our gold mine for the AI.
Which brings us right to Section 3, Deep Learning, the Artificial Neural Network Design.
So how do you actually teach an AI to understand and instantly predict all that incredibly complex, multidimensional solid mechanics data? Well, here is the architecture they finally landed on after rigorous testing. Because of the inherent linearity of the problem, they utilized a feed-forward deep neural network. It takes in 12 input variables. These are the microstructural properties we were just talking about, like fiber volume fraction, modulus, and the specific components of that orientation tensor. It takes all of that, processes it, and spits out 21 output variables, which fully describe the complete composite stiffness tensor. And by using a grid search hyperparameter tuning technique, they found the absolute optimal sweet spot for learning. 3 hidden layers with 25 neurons each, utilizing exponential activation functions and the highly efficient atom optimizer.
And guys, the results of this training phase were absolutely phenomenal. The model achieved an incredibly low root mean squared error, or RMSE, of just 0.0046 during the testing phase. Now, to put that into perspective, this tiny error rate demonstrates that the deep neural network didn't just memorize the input data. Oh no, it achieved a profoundly high interpolation capability. It actually learned the physical underlying relationships within this vast, multidimensional parameter space. It's a real game changer.
Let's move on to Section 4, Validation, Proving the Model's Accuracy.
Now, you might be wondering, how does a low mathematical error actually hold up against rigorous mechanics and real-world materials? Well, Figure 10 provides some sheer visual proof of its accuracy. We're plotting the ANN's predicted values on the y-axis against the expected micromechanical results on the x-axis for the primary Young's modulus, E11. Take a look at both the training data on the left and then the completely unseen testing data on the right. Notice how the data points just perfectly hug that center trend line? That incredibly tight correlation you see right here is proof that the network handles the physics flawlessly. Next up, Figure 11 analyzes the Young's modulus in the transverse 2 direction, or E22. And once again, the predictions just align beautifully with the expected computational results without any sort of excessive scattering. This really confirms that the model handles the complex, multidirectional elastic tensors of the composite material. And honestly, this is a fact that's further validated in the paper by Figure 12, which flawlessly predicts the in-plane shear moduli too. It's hitting the nail on the head across the board.
But to truly prove real-world applicability, the researchers didn't just stop at digital simulations. Here we have a table highlighting experimental validation data from the literature, testing the network against physical glass fiber reinforced polyamide 6 composites, specifically PAGF15 and PAGF30. These were real-world plates that had complex orientation distributions. Now, while this table gives you the basic parameters, the researchers actually used figures 13, 14, and 15 in their study to graph the ANN's exact performance against this experimental data across various cut angles relative to the injection flow. And guess what? It successfully and accurately predicts the real-world lab tests. No way around it. It just works.
Which leads us directly to the author's ultimate conclusion, as they state right here. The ANN model gives reasonably good predictions for the elastic properties of short fiber reinforced composites. It's an objective, fully validated confirmation that this rapid, data-driven ANN model is a highly valid replacement for those incredibly costly and time-consuming micromechanical computations we were discussing at the very start of this explainer.
Section 5, Practical Applications and the Future of Solid Mechanics.
So what does this all mean, and why does this matter so much for the broader engineering community? Well, the future implications listed here are absolutely massive for industrial design. Because the neural network takes literally just fractions of a second to compute what used to take hours of direct simulation, this rapid model can now be seamlessly incorporated into full-scale, real-life structural analysis. I mean, just imagine designing an entire aerospace component and instantly knowing the exact stiffness of the composite at every single mesh point based on the local fiber flow. Furthermore, the team notes that this foundational framework can be extended in the future to include even more complex phenomena like matrix inelasticity and matrix fiber debonding. Finally, we definitely want to conclude by acknowledging the Mechanics and Physics of Materials research group at materialslab.org for this incredible foundational work. By brilliantly merging deep learning with rigorous two-step micromechanics, they've completely changed the computational speed limit for material analysis. So I'll leave you with this final thought to chew on. If we can now accurately predict mechanical stiffness in milliseconds instead of hours or days, just how much faster will the next generation of advanced, lightweight materials be engineered and brought into the world? Thanks for joining me for this explainer, and I hope this sparks your curiosity to keep exploring the absolute cutting edge of material science.